Hello everyone, welcome to my video. In this video, we will go over basic concepts in chapter 4 about kinetics of systems of particles. This is going to be a bit different than we normally do. The content in this video will not be discussed in lectures, as these sections served as linking what we have learned seeing motion as a particle to analyzing a system of particles. Later on in this course, we'll do lots of examples that uses the system of particles concept. So you will have plenty of chance practicing questions related to system particles. Therefore, we are not going to spend a dedicated lecture to do examples for section 4.1, 4.2, and 4.3, since many examples later on use the same concept. For those of you in my class, there is a video going over 3 examples in chapter 4. The link is provided on Learn. You should treat them as important as those we do in lectures face-to-face, so please watch them. If you recall, we started with Newton's second law. As I said, its entire course is around F equals to ma. We did work and energy, impulse and momentum, and then conservation of energy and momentum. All of these were built on one important assumption. The object can be treated as a particle, such as the baseball here. Let's look at this baseball closely. We will zoom in to look at a single particle or a single atom on this baseball. This is not a simplification. We are essentially looking at a single particle. We can set up an xy coordinate system and use vector r1 to represent the position of this particle related to this origin O, the xy system we set up. From outside, that's from the baseball bat, there are forces being applied to this particle. Let's say F1, F2, F3 here. We use capital F. Just pay attention to that. From the inside, in the meantime, due to the constant motion of particles, there are forces applied to the particle from the inside. Let's say F1, F2, F3 here using the small f. Now if we apply the Newton's second law, F equals to ma here, the particle is experiencing the overall force. We can write F1, F2, F3, all capital, plus small f1, small f2, small f3. All of them adding together is a resultant force. Adding together, that is equal to, according to Newton's second law, equals to F equals to, sum of F equals to ma1. This a1 just means this particle, I'm just naming this as a number 1. Okay, that's one single particle. Now, repeat this process for all particles within this entire boundary, which is the baseball, right? Using the Newton's second law, we're going to have all forces adding together equals to sum of m of one particle times the second derivative of the displacement, which is the acceleration. Right? This I, little I here, let me bring my laser. This I here is really just representing one particle. On the previous page, we used 1, right? That one single particle. In this case, within this entire boundary within the baseball, we have numerous, countless, or countable. Okay, we have lots of particles all add up together. This I is from 1 to whatever that big number is. Okay. If we look at the mass center G here for a moment, using R bar, it's also a vector to represent the location of the mass center G. And then we multiply this R bar with the mass M, the total mass. This is equivalent to the total mass of the entire object or the entire baseball. By summing all particles that consist of the baseball. Okay, so we have the mr bar is the same as adding everything together, all the particles, all atoms together within that baseball. Okay, they are equivalent, left-hand side and right-hand side here. Therefore, when we take the second derivative of the displacement, and then we'll get on the left-hand side, we have mr second derivative. On the right-hand side, we're taking the second derivative as well. So this is the same as what we have before. Sum of mi, ri, second derivative. The summing of every individual particle, m times a, for every individual particle. Okay, let's put everything together here. All forces every particle experiences, external or internal, all add up to this sum of mi, ri, second derivative. But don't forget, when we are looking at an object at a macro scale level, the large level, all internal forces are summed to 0. As well, from the previous slide, we obtained this mr bar second derivative equals to sum of mi, ri, second derivative. This brings us the generalized Newton's second law. For a moment, you'll realize this looks the same as what we already know. Sum of F equals to ma, except there is a bar here. We call this equation the equation of motion. This equation tells us that the resultant of all the external forces on any system of masses or any system of particles equals to the total mass of the system, m, times the acceleration of the center of the mass. Remember, r bar representing the position of the mass center g. So we have a bar here, the acceleration of the center of mass. However, there is a caveat. This is an instantaneous relationship. Remember how we set up the boundary at the beginning to look at the one individual particle right here. Because the boundary may change due to deformation, right? When the ball is hit by the baseball bat, maybe the deformation will be small, but there will be some kind of deformation. That means the location of the mass center G can also change, whether it's a large change, large difference, or small difference, right? It can change. So this equation of motion we have here, the sum of F equals to ma bar, must be updated as soon as these parameters changes, right? Or this equation can only describe an instantaneous relationship between sum of forces and the acceleration. So what we have done here in this section 4.2 is to generalize Newton's second law from a single particle that we have done this so many times before the midterm to any system of particles. Now we focus on the motion of the center of the mass using the total external force and the total mass. And internal forces cancel out each other and don't affect the overall motion. Okay, one example here on the screen, you can see on the right. We have two blocks. Let's say we have these two blocks representing some kind of object, and that object is by chance only have two particles consist of that object. Okay, so we have these two blocks. One has 3 kilograms and one at 2 kilograms, and they are connected by a spring. Think of them as two individual particles, as I said, within a big system. Okay, within the system boundary here. Therefore, when we're looking at them from the system level as a whole, when there is a 10 newtons force pulling the system, the acceleration can be calculated as F equals to ma, where our total mass is 3 plus 2 is 5 kilograms, then we can get the acceleration is 2 meters per second square, right? 10 divided by 5, which is the acceleration of the center of the mass g of the system. And you can see that even though the spring causes, and of course it will cause internal forces, either pulling or compressing between the particles, between the two blocks, these forces won't influence the net motion of the system, right? This is where we're defining our system is. We're just only looking at what is the total external force applied on this system. Whatever is happening inside is not going to affect our net motion of the system, okay? Looking at these two things together as a system. Therefore, let me remind you that Newton's second law relates force and acceleration. And both of them are instantaneous. And this is by definition. Force F is the push or pull at a specific moment, and acceleration A is how fast the velocity is changing at that moment. Okay? What I just said, a specific moment and at that moment. And they both are functions, can be functions of time t. So their relationship must be evaluated at the same instant. Okay, what that means is, I have an example here. Either at the instant of 0 second or 10 second, here or here, this equation sum of f equals to ma bar is valid. Right? You can calculate the acceleration of these instants at 0 or at 10, which is the acceleration of the mass center of the shopping cart. However, what you cannot do is taking the difference between the acceleration at 0 second and 10 second, then divide by 10 second to get the average acceleration. Because this is fundamentally wrong. Because the average force is depending on the integral over time. Remember the ft integral we did over in the previous chapters? So the acceleration is not necessarily linearly related to the force unless the force is constant. And in this case, apparently it's not. The force is from 5 Newton to 10 Newton. You don't know what's going on between 0 and 10 seconds. But all you know is the force is not a constant in this case. So the system is not responding linearly over time due to the changing conditions. In this case, the external force is not a constant. And sometimes you have variable mass, you have variable friction, you have variable other constraints, such as air drag force, if for some objects that is flying. So to put everything in a single statement, you cannot take an average of acceleration. Okay, let me repeat again. You cannot take an average of acceleration. So we talk about forces. Now we'll look at energy. Okay, once you understand what is going on with the force and the generalized Newton's second law, sum of F equals to ma bar, which is summing all individual particles within the system, gives the status of the system. You can recall what we had in chapter 3. The total energy from one point to another is the change of kinetic energy. Right? This is what we learned in chapter 3. Now, think about the total energy of the system can be calculated by summing the change of each individual particle. Let's call this, each one is I, in the system. That is, the U, the total energy from point 1 to point 2, is equal to sum of every individual particle, the work done from point 1 to point 2. Then the total kinetic energy is a sum of work done by all forces, external and internal, on each individual particle. Now, from each individual particle's perspective, the kinetic energy comes from two components. 1 is the absolute velocity of that particle, 1/2 mv squared. Okay, this is 1, wherever the particle is, and then the motion of each particle relative to the mass center. And this is being calculated by 1/2 mi rho I dot square. Okay, this rho I is representing where that particle is relative to the center mass g. Okay, rho is the same as vector r. It's a displacement vector, and the derivative of that is the velocity. Okay, this is still the 1/2 mass times velocity square term. Okay, you have two terms to consider for every particle in that system. However, you also need to remember work energy is just one application using the generalized Newton's second law. And there are many other applications, but we're not going to spend times on that. For this chapter 4, what you need to get is this work energy equation. And previously we'll talk about the generalized Newton's second law. The examples of applying this generalized Newton's second law are in a separate video, so please check it out. If you are in my class, you can also find the link on Learn and on your weekly checklist. Okay, so here is the recommended reading list. Please take a look. For sample problem 4/1, you only need to know up to how t is calculated. And for sample problem 4/5, only part A is required for you to know. Thanks for watching. I'll see you next time.